I'll next call upon our last speaker for the today's session, Dr. Jean Mulopo from University of Witwatersrand. He is currently an associate professor in the University of Witwatersrand in the Department of Chemical and Metallurgical Engineering. He is also coordinator and head of Sustainable Energy and Environmental Research Unit. And his research is mainly in the area of pollution and water-based research, as well as on waste-to-energy research projects. Dr. G, can you join? Can you share your screen?
Good morning, Chair. Can you see my screen?
Yeah, I'm able to see the screen. Yes, yes.
Okay, thank you very much.
Floor is yours. Yeah.
I'd like to thank you, Chair, for the opportunity to present to this conference. I'd like also to extend my deepest thanks to Prof. Majosi and Prof. Raj for this opportunity to present in this forum. And I think, being the last speaker, I'll try to be as short as possible. And I think the distinguished speaker came before me and summarized most of the work I do in this particular area, particularly around acid mine drainage, as highlighted by the speaker from the CSR, but also by all the other speakers came before me. So today, I will share with you my talk will be around the water and energy. Thank you, Chair. So I was saying that today my presentation will be around the water and energy nexus and some of the perspective on the experimental analysis we've done around using membrane technology in the treatment of acid mine drainage in South Africa, particularly. And as I said before, my presentation will be quite short, but what I'll try to do is to give a perspective on the acid mine drainage challenge we face as a country in South Africa, some of the solutions which have been proposed, and how membrane technology has been used as a viable option, or the most viable option in this case, and some of the gap and opportunity for energy and water integration in order to make the existing implemented technology more sustainable. So as Prof. Raj said yesterday, I think we had an issue of water around the world. This is a map which was shared by the University of Kassel in Germany, for which is really a projection for 2020. That was last year or 20 years ago. And you can see clearly, and I think the same map was also shared by Prof. Majosi this morning. You can see clearly the red zone are the zone which are very stressed in terms of water. And this is the same map in 2050. So 25 years from now, this is how it looks. You can see how the red zone extends for most of the country, including the south of India, and also a large chunk of the South Africa as well has moved to red in terms of water availability, etc. And in 2070, this is how the map will look even more. So the situation as we move forward, as highlighted by the previous speaker, becoming even more drastic. And so we need to take measure on how we manage the little resource of water we have available in our countries. So let me now talk about the MD challenge, particularly in South Africa. And I think though the mining industry use only a small fraction of water, as alluded by Dr. Harrison as well yesterday, but it has a significant impact on the quality of underground water and the water resources available in the country. Around the year 2000, I think we had around the Western Basin and the Central Basin decaying of acid mine water drainage into a surface stream. And because mostly of many mining activities stopping and mainly closure of many mining activities in the region around the West Basin. And so what happened is that we have this massive decay of acid mine drainage in those particular areas. And the AMD itself is a very poor quality water, and it had serious threat, it posed serious threat to the ecology, but also to the Vaal River system. The Vaal River system is at the heart of rainwater rainwater being one of the biggest bulk water utility in the country because it serves the greater Johannesburg region, which comprises not only Johannesburg, but also Pretoria and the municipality of Ekurhuleni. And that represents around probably 20% of the South African population, because this is a very, not only industrial zone, but very populated area as well. And so it poses a serious threat to the water distribution and availability in the country. And because of that, and I think a number of solutions, high levels, before and because of that, and I think one of the second challenge was the financing model as well available to the country. What's happened is that because most of this can't happen after the mine have closed, after the closure of this mine, so the remediation cost of most of these, of the mine water drainage, acid mine water drainage, is an external cost most of the time, which have to fall on the public, the taxpayer, let's say the taxpayer. And this, in a sense, have been for activists and social stakeholders, have not boiled very well with them, because they feel that they have to take the weight of fixing the problem while the mining company have closed and have taken away the profit. So nevertheless, two solutions have been proposed at higher level at higher level of the country. The first one is what we call the short-term solution. The short-term solution is mostly about using the HDS process. The HDS process stands for the high density sludge process. Is mostly a neutralization process, meaning that just increase the pH and precipitate some of the heavy metal within the acid mine drainage stream, and then the water is then discharged to the water bodies or the river stream, the surface water stream, etc. The challenge of that solution, that proposed solution, though it is very well established and quite cheaper, or at least the process is well understood and extensively used, not only in South Africa, but in Australia and also in Canada. It's quite old process, flexible as well, can be used for small companies, but also for large-scale companies. It has a challenge that it does not provide a desalination of the acid mine drainage. And desalination is a serious threat for the water system, particularly the rivers and the streams in the countries. So in a nutshell, though the HDS process is quite well established and well understood and easy to implement, it has two major drawbacks. The first one is that it does not desalinate the water. But the second point as well is that it generates an amount of sludge which still need to be disposed of at a higher cost in a sense. So this is the plant which has been built recently, I think past 2020. I think it was an existing plant which was then expanded in order to cater for the additional decant which was happening around the central and the western basin, particularly. So it's a simple plant, but based on the HDS process, which is the neutralization. It uses limestone as well, a combination of lime limestone to treat the acid mine drainage and generate the sludge. But the second solution, which was proposed on top of the previous solution, which was a short-term solution, was called the medium and long-term solution. And the idea behind this proposition was to provide an alternative or a pathway for desalination, because the previous solution, the HDS process, could not cater for desalination. So what the country thought was to say, can we think at a long-term solution, which will only not will do the neutralization phase, but also do the desalination phase. And for that, a number of solutions have been looked at, both by the private sector in the country, but also by the public institution in the country. And I think private companies like Avenge, like Veolia, Kipling, and on the public sector, we had CSR, Mintech, and many other institutions and universities as well, have tried to look at different solutions in order to provide long-term solution in terms of desalination. Some of this proposition or technology proposed were the physical processes, membrane-based technology, and then we had a second vague of proposition, which is the chemical processes. The chemical processes were proposed by the CSR and Mintech, and quite successful as well. And then we had also proposition in terms of biological processes. Here I just named few of them, but they just quite a number of them, not only in the country, but also outside the country, which were tested and at a lab scale, and sometimes also at pilot scale, in order to assess their viability in terms of treating. But what came up of that exercise is that the membrane-based technology stood up as the most viable technology in terms of treating acid mine drainage to a drinking standard. And here I want to insist on the word drinking. And I think though some of the technology like the biological process and the chemical process could provide some kind of relief in terms of desalination, membrane-based technology stood up as the only technology currently to be able to provide water of drinkable quality. So in that regard, I think some stakeholders, some mining companies and some municipality put their hand together in order to try and implement the membrane technology, particularly the reverse osmosis technology. And I'll show you some of the application just now. But before I show you some of the application just now, I'll probably like to point out two of the issues which came up with that, the reverse osmosis technology, which was the most established among the membrane technology. So it was first used for acid mine drainage in the coal sector, the coal acid mine drainage, because there seemed to be a difference between the coal acid mine drainage from the coal industry and acid mine drainage from the gold industry. And in terms of composition as well, in terms of toxicity, these tend to be different. But this may also do because of the geology of the terrain where this mineral is extracted. The coal mine, which are mostly located around Mpumalanga, whereas the gold mine are mostly located around Johannesburg area and the Western Basin area. So what happened, two conclusions came up from that is that the RO process seemed to have a large footprint in terms of capital cost. That's established, and I think the previous speakers also highlighted that fact. It's also very energy intensive. That's not a secret, and I think both speakers this morning highlighted that fact. But it also generates an extensive amount of brine, which still need to be disposed or treated in one way or the other. So nevertheless, I think stakeholders in the country went ahead and implemented the reverse osmosis processes. It was first implemented in the Witbank area, the eMalahleni Water Reclamation Plant. That's a quite huge plant. I think the first phase of the plant treated 25 megaliter a day. That's quite extensive. And later, because of its success, the plant was expanded to 60 megaliter of water a day. And the water recovery was around 99%. And that's quite remarkable, really, in terms of. So the quality of the water itself met all the standard, the South African standard, as required. And for that reason, because the plant was a joint venture between mining companies and the public sector, then they decided that the water could be sold to municipality, a local municipality in the Witbank area. So the plant was a success. That's the picture of the plant itself. And it has been in operation for the past probably 20 years, if I'm not mistaken, and expanded to 60 megaliter recently. But it's quite a success story in terms of providing water, in terms of recovery or of acid mine drainage for drinking water, which is sold to municipality. A second example, I think there are other example, but I chose two examples just in sake of time. The second example is a 15 megaliter plant, which is called the Optimum Water Reclamation Plant. And again, that's the similar story. The water from this plant is also sold to local municipality. The recovery ratio is quite high, 98%, and still the same challenge is faced by the plant as well in terms of the brine generation, which need disposal at a relatively higher cost as well. So a point I wanted to share with you is that, as I said in my previous point, is that there were a number of technology which were proposed in this slide here, the chemical technologies, physical and biological. I wanted to do a simple exercise and provide a quick running cost and to see how this technology ranked in terms of their profitability. And the data used come from different institutions, from the CSR, from Mintech, and some from literature, just available literature. When you look carefully at these, you can see clearly that all the solutions proposed are not profitable, or some are less profitable than others. And you can see that the CSR ABC process stand quite well, I think. The difference is minus 0.49, whereas the reverse osmosis technology, because what is happening is that the membrane technology, sorry for that, I think I pressed the wrong button. The membrane technology still use a portion of the chemical technology upfront for the pre-treatment phase, because it has to remove some of the most the sludge within the water before the water is fed to a membrane to the RO process. So most of the reverse technology as it's used in the mining sector is that you have a chemical processes, a neutralization phase upfront, where you do part of the neutralization to increase the pH, but also precipitate some of the heavy metal, and then so it carry a bit of the cost of the neutralization phase in a sense before it goes to reverse osmosis process. So in that regard, also you could see that the margin profit is quite negative, and that the reverse processes as implemented, at least in the mining sector, seem to be the less profitable of all processes, existing processes, including chemical and biological process, because the bioshow is a biological process. So I put there for sake or so looking at it. And the last processes is the pH neutralization process, where you only do neutralization without further treatment in terms of that. So you could see clearly, so what is happening is that though the water is sold to local municipality, and because of the negative, there is no profit, it means that there is subsidy which has to be provided by the government or the public sector in a sense to carry the operation of the plant. So the plant is running at a negative cost in a sense, really. So my thinking, and that's what I wanted to share with the audience this morning, is that there is opportunity really to improve on that, on the overall cost of the RO process, as it has shown potential in terms of the water recovery. And it has been, at this point, one of the most sustainable technology, or the success story in terms of recovering acid mine drainage and providing solution to some of the municipalities which are stressed in terms of waters. So we could do, as Prof. Majosi said this morning, look at process integration. The process economic itself is driven mostly by the recovery ratio, which is the ratio between the feed and the permeate coming out of the membrane. It has been shown in literature most of the time that as the pressure increases, the recovery ratio also increases. But if you increase the pressure, you also increase the cost, the energy cost. So you need to find the trade-off between these parameters. But my point really is that there is opportunity for process integration, optimization, in order to find to recover energy within the process. I'll come to that slide at a point. But what I wanted to share here is that if you look at the cost distribution within the plant as it stands, you find that the membrane replacement cost and the energy cost, the electrical power cost, stand out respectively at 30% each. I think 25% for the membrane replacement, 30% for the electrical power, and 30% for the fixed charge. So the fixed charge, we can't do more about it, but I think at least on terms of the membrane replacement and the energy cost, we have at least 55 or 60% of the overall cost of the plant. And those two areas, I think there's opportunity to do something about it going forward in term. So one of the area of energy integration opportunity in order to improve the cost efficiency of the RO process as it is implemented in the mining sector, I thought will be, for example, energy recovery from the high pressure brine coming from the membrane toward the low pressure feed water. So there is a potential there, and most of the research is done, as Prof. Majosi and Prof. Roger indicated, and I think it's a good opportunity. I'm not sure how much work in terms of integration, energy integration within the RO process as it's integrated in the mining sector is done really to find any opportunity for energy recovery. But I think it's an area which is worth exploring, and so that we can improve the cost efficiency of the process. Another area which represents a huge opportunity will be, in my view, to look at a new membrane material which can withstand falling as indicated previously. And I think the cost of membrane replacement stands itself at 30% of the total energy cost within that industry. So finding way of developing new material for better membrane would be also an opportunity to improve on the energy cost within that industry. And I think that's what we have done. We did look, my research particularly, I think Prof. Majosi and Prof. Raj research will probably look at how we do energy integration better within, and where are the opportunity to recover energy and reuse that within the system. But we look particularly what will be the opportunity of synthesizing new type of membrane which can withstand falling within the system, etc. So what we did in the lab is that we synthesized a new membrane. It's a polysulfone membrane, and we use as a substrate the carbon nanotube. So we synthesize the carbon nanotube using the CVD method, and once we synthesize that, we then functionalize the carbon nanotube itself. These are some of the picture of the carbon nanotube we have synthesized in the lab. And after we synthesize that, we use two techniques really to produce the polymeric membrane. We use what is called the phase invasion method and the solution casting method. I'll not dwell in the details of that, but these are the two FEM image of the two membranes we've synthesized. On the left, we have the membrane which was synthesized using the PI method, and on the right, we have the membrane which is synthesized using the casting method. And in our view, we thought that the casting method provided a more structured membrane, as you can see on the right, than the left one. And we use this casting membrane, or the membrane obtained using the casting method, to test it on the brine, because one of the key challenges I've indicated of the mining industry is that of the reverse osmosis process as it is implemented in the mining industry, is that it generates an extensive amount of brine, and that brine needs to be disposed. And in the long run, it becomes a liability, really, because the plant is running out of disposal space. There have been few solutions, really, which have been looked at in order to treat that brine. I think one of the solutions which came out was proposed by the University of Cape Town. I think it's called a freeze desalination, freeze detecting method, if I'm not mistaken, or something like that, but have not been fully implemented, probably is in testing mode. And I think there's also some other solution which is proposed by the industry, but not yet fully implemented. So we want just to say, can this new type of membrane we produce be able to treat the brine without any additional, incurring any additional high pressure? As the previous speaker also highlighted, that because the concentration of the brine is quite higher, you need a very high pressure in order to treat it using reverse osmosis membrane. So we wanted to see if the new membrane we're synthesizing in the lab could be used to treat effectively the brine, but at a lower pressure. And that's what we did. And I think we used, these are the results. We got the ion rejection standard at 87.2%, and the flux is given to the right, And this is the ion rejection. And I think we just indicated the summary on the previous slide. But also we looked at the separation of the various ions within the brine. We looked particularly, I think there are a number of, to be fair, there's a number of components within the brine, because it comes from mining activities, but we selected some of the key ions we thought were quite prevalent. And the brine is quite rich in sodium sulfate. It also contains a substantial amount of sulfate, and which is really the key for desalination, the salinity of the brine. I think the sulfate contributes to more than 60% of the salinity of the brine. And then we have magnesium and calcium, etc. And then we looked at their separation from the brine. These are the results. You can see that the membrane was able to...
Sorry to interfere, Dr. Jean. Can you wind up in 2 to 3 minutes, if it is okay?
Okay, thank you, Chair. Thank you, Chair. I'm almost at the end of the thing. So you can see clearly that the membrane was able to remove most of the ion, including the smaller ion like the sodium and the potassium as well, which stand at 25, 26%. So this has come to the end of my presentation. I think, well, just to give a perspective, and I think the previous speakers have said it all in a way or in the other and differently. And I think going forward, I wanted just to show the opportunity of integrating energy and water within the mining sector using the RO process, because probably this is one of the most established technology in terms of water recovery from acid mine drainage, and it represents a viable solution going forward. But its large footprint in terms of capital cost, its negative profit pose a challenge, and the amount of the brine release still pose a challenge, and those by themselves represent also opportunities for process integration, but also development of new membrane technology material or composite membrane material, which can be used successfully to treat the brine and alleviate and improve the RO process as it is established in the mining industry. So on that note, thank you, Chair, for the opportunity, and thank you for everyone.
Thank you, Dr. Jean. Thank you for a wonderful talk.